Hey guys, I'm going to go ahead and do this example from our notes, finger length. The first thing I did, which I did this before I started the video, is to just find the, I guess I'll read the problem, even though I know you can read, but sometimes you don't. Is your index finger longer than your ring finger? Does this depend on your gender? A random sample of 460 high school students in the U.S. was selected and asked to record if their pointer finger was longer than, shorter than, or the same length as their ring finger on their left hand. The gender of each student was also reported. The data are summarized in the table below. Hey, you should check yours. My ring finger is longer. So look at your left hand. Is your ring finger longer than, shorter than, or the same length as your pointer finger? Leave the results in the comments. It'll be super fun. Okay, anyways, moving on. So, I apologize, because I think on your paper that this space is actually super small. So draw your graph as small as you can. But as we make this graph, we don't want to compare the counts. Again, I think we talked about this another time, but these totals are different. Even though they're pretty close in this one, they are different. So we want to compare proportions, because that's the only way to really kind of see apples to apples, or like compare them fairly. So this proportion, this is 85 out of 227 was 0.374. This one's 0.185. 0.441, 0.313, 0.189, and 0.498. So again, I just got those from dividing, like 73 divided by 233 is 0.313. So those are the proportions. So for my graph, I'm going to make a bar graph. Again, you're just going to have to draw yours smaller because on your paper there's not as much space here. So across the bottom, just like the other ones, there are multiple ways you could set it up. I'm going to set it up where I do, all right, I'm going to call this IF, IF, S, and RF. That doesn't matter what you call them. But if they're labeled up here, then it's pretty easy to see what you're talking about on your graph, and you don't have to write out these whole long statements. So I'm going to have for each one IF, S, and RF. And so this would be for female. And then I'll have 3 more over here. IF, S, RF for male. And then I'm going to put my proportions over here. So, and the title, I guess I can do, I don't know, relative finger length or finger length. It's always good to have a title though. So over here, I'm just gonna, the biggest one is just under 0.5, so I'm just gonna make 0.1, 0.2, 0.3, 0.4, 0.5. And then I'm sure all of your graphs are going to look much better than mine, but we're just making a bar graph for the two different, or like bar graphs for the two different groups. So for index finger, that's 0.374, somewhere in there. Same 0.185. That one, 441. Okay. And then over here, I'm going to have 0.313. And this one, those are almost the same. Those two are really close, so this one will be just a little, such a tiny little bit bigger than this one, but they look essentially the same when they're drawn. I don't know, maybe it's easier to see these if I shade them. You can also do what we've done on some of these is like color code. So say over here, like male is red and female is blue or something like that. It doesn't matter. So there are a lot of ways you could display this appropriately, but no matter what you do, you should have bar graphs. And RF, so ring fingers longer, 0.498. And if I wanted to give a statement that would explain describing what I see, the distributions are fairly similar in that the lowest and the highest are the same for both, right? These two are almost identical. Over here we have index finger being longer is a little bit more likely for females, whereas ring finger being longer is a little less likely, and vice versa for males. So that's going to be the main difference we want to note. Not toest, the lowest. I don't know if you needed to write necessarily all of that. I was kind of trying to write all of what I saw. But again, your paper, I'm pretty sure that I gave y'all one where that was smaller because my original was. But yeah, sorry. But that means I'm going to have less space here, and I'm going to have to write really small because this part B, do the data provide a convincing evidence at the alpha equals 0.05 level of an association between gender and relative finger length for high school students in the U.S.? That's a whole state plan do conclude. So I'm going to start out my state. So remember that in this section, the state step for chi-squared for independence or chi-squared test for association, both of those names are appropriate. I think the book generally says for independence though, but those are the same type of test. Yeah. So here's what we wrote in the notes about this. We said there's no association between two categorical variables in the population of interest, or there is. So the two categorical variables here are gender and relative finger length. So that's what we're going to write as our hypothesis. We'll say our H null is that there's no association between gender and finger length for U.S. high school students. So, and then HA, there is an association between gender and finger length for U.S. high school students. Okay. Questions? No? All right, cool. Let's keep going. Plan. Well, this type of test is a chi-squared test for independence, or test of independence. You can also do test of association. Either one is appropriate, as I said a second ago. Checking conditions, random. We were given that it's a random sample of 460 high school students in the U.S. %. Remember, for the 10%, generally we're just multiplying our sample size by 10 and saying that there are at least that many individuals in the population. And so what I'm going to say here is that there are more than 4,600 U.S. high school students, which is pretty obvious, right? We have more than that in just San Antonio. And then our expected counts is the next one we need to do. For large counts, remember that each of our expected counts need to be greater than or equal to 5. It seems pretty obvious that they will be here, given that the original ones are so close. But just like with the other two-way test we did for homogeneity, I don't want to by hand average these two and then multiply by each of the totals and figure out all those. Even though it wouldn't take that long with just 6, it's still just so much easier to do it in the calculator. And so that's what I'm going to choose to do here. First, I'm going to go ahead and define my matrix. This was the piece that some of us were forgetting in class today, where we say, I'm just going to call this finger, which is kind of a funny thing, but it's what the problem's about, so. Okay, so control and then the matrix button, and it should look like that. It'll give you a little colon and then an equal sign. And then push the matrix button again. Select this one that's already been selected here. It looks like a 3x3 in the picture, but that's the only one of these matrices that will allow you to choose the number of rows and columns that you want. So I have 3 rows and 2 columns. Oop. Every time. Okay. And I'm just pressing tab between each one because that will take me to the next box. Okay. It's been saved. Then I'm going to go ahead and run my test. I think we're all pretty comfortable with the menu with this, but definitely let me know if you're not. We've done all of these by this point, but we're down here at chi-squared two-way test. Observe matrix, finger. Okay. Remember, to get my expected matrix, I'm going to need to hit VAR, open up my expected matrix, and I'm just going to copy those down and show that they're all greater than or equal to 5. and those are all at least 5, so we're good to go ahead and move on with our test. So in the do step, I've actually already done it, right? It's in the calculator. But what I am going to do is I'm going to write out the first term of my chi-squared sequence, because I know that those are calculated using the sum of each observed minus expected squared over expected. So I'm going to at least write out the first term. Plus dot 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 equals 2.065. All right, and then degrees of freedom. Again, those are in the calculator, it's 2, but it is rows minus 1 times columns minus 1. This is 2, this is 1, so it's 2. And the p-value, which I also just get from the calculator. It's right here, 0.356. Okay. Excuse me. Okay, so that p-value is pretty large. We were given an alpha, so we'll use that, but since our p-value of 0.356 is greater than 0.05, we fail to reject. So that means we do not have enough evidence, or we don't have convincing evidence of HA. Okay, hopefully you can read that, but it says, since the p-value of 0.356 is greater than alpha of 0.05, we fail to reject H null. We do not have convincing evidence that there is an association between gender and relative finger length for U.S. high school students. Okay. All right, if your conclusion in part B was an error, which type of error did you commit? Okay, there's only one possibility here. And I think maybe some of us have forgotten what these really mean. So I'm going to draw this little box over here that was in our notes a long time ago in chapter 9, but I'm not sure, I feel like a lot of people have forgotten. So, when you conclude something, there are 4 possibilities. First, there are 2 ways that you can write your conclusion, right? Either you reject H null, or you fail to reject H null. Okay, so those are the 2 things that you can do. The 2 possibilities in the real world outside of this are either H null is true or H null is false, right? Now, we never actually say that H null is true, right? In our conclusions, we'll always fail to reject. We don't accept, but you know, in the real world scenario, it could be true, right? So if we reject H null and H null is true, then we have committed a type 1 error, If we reject H null and H null is false, then good, that's what we wanted to do, right? That's correct. If we fail to reject H null and H null is true, well good, that's what we wanted, right? Fail to reject, right? So that means we don't have evidence for HA. So if H null is true, then cool, we did it. We got the right answer. If we fail to reject and H null is false, we've committed a type 2 error. So when you fail to reject, the only possible error you could have made is a type 2 error. When you reject, the only possible error you could have made is a type 1 error. And that makes a lot of sense if you go back and you remember that alpha is actually equal to the probability of a type 1 error. So something that falls in that rejection region, we would reject, but it does happen by chance 5% of the time, and that's when it would be a type 1 error. So in this case, we failed to reject. So we could have committed a type 2 error. And that would happen if there truly is an association between gender and relative finger length. Okay. All right, so now would be a really good time for you to go ahead and take out checkpoint 4 and complete that, because that's gonna follow kind of the same process that we went through here. So if you learned something new from this video, then be sure to like and subscribe. Thanks, guys.